Hello students, this is the last part of my series of tutorial lectures. This time I'll be discussing questions related to electric potential energy and electric potential. So how do we relate the amount of work done on a given charge and the electric potential energy that the charge acquires? So let's consider this diagram. It shows a test charge Q naught is within an electric field. There is an electric field between two parallel charged metal plates. All right, here's the positive metal plate and the negative metal plate over here. So the electric field that is within this two charged metal plates is said to be constant, and the direction is from the positive charge plate to the negative charge plate. Okay, or in using our perspective, we can say that the electric field is downwards. And imagine that the test charge Q naught starts from point A. All right, point A is closest to the positive charge plate, and it starts to move towards the negative charge plate, labeled here as point B. Okay, so we say that this test charge experiences an electrostatic force F, which is equal, okay, to the product of the electric field, the magnitude of the electric field E, and the amount of charge Q naught. So we have here the definition of that force F. And we also describe the amount of work done by the field on the test charge. We say that the amount of work done, okay, in moving the charge from point A to point B, it's denoted by this symbol WA, okay, A sub A towards B. That is the work done in moving the charge from point A to point B is just equal, all right, it's just equal to the change in the electric potential energy denoted by negative delta U, which is in fact just equal to the amount of work done, all right, whose definition is equal to the product of the force F times the displacement, okay, indicated here by the letter D. All right, so if you multiply the force F, the magnitude of the force F multiplied by the displacement D, and they are in the same direction, we say that the work done is a positive work. All right, but that corresponds to a negative change in what we call electric potential energy of the charge. Okay, so that is summarized in this paragraph. When a charged particle moves in an electric field, the field exerts a force that can do work W on the particle. This work can always be expressed in terms of the change in electric potential energy, delta U. All right, so the formula that relates the work done on the charge by the field, okay, its relationship to the change in electric potential energy, delta U, is shown in this equation. Delta U is equal to the work W, okay, from A to B, which is equal to the product of the force and the displacement, and in terms of the charge Q naught multiplied by the electric field, all right, and the distance D. May I also emphasize that the force is said to be conservative. Okay, the electrostatic force that the test charge experiences as it moves within an electric field, earlier described, This work, labeled as W sub A to B, okay, which is the work done by the field, is independent of the path that the particle takes from A to B. So as shown earlier in the diagram, regardless of the path taken, okay, the amount of work is always equal to this formula defined in terms of the charge Q naught and the electric field E, regardless of the path taken. That is what we mean by the force F being conservative. So this reminds you probably of the uh, what do you call potential energy that is acquired, gravitational potential, and that is acquired by a given mass when work is done on that particular mass, okay, in moving it, okay, say for example from the ground to a certain height, okay. So regardless of the path, we always consider the vertical height, okay, as the displacement. So that also applies. The concept of the force being conservative is also applied here. So with this as the work done by the field, we also have the expression for the potential energy uh, delta U. All right, delta U is equal to the product of the charge Q naught times the electric field and the displacement D. And regardless of the sign of a charge Q naught, okay, we have this sign convention, okay, or agreement. If the electric potential energy increases, okay, it means that the test charge Q naught is moving in the direction opposite to the electric force or direction of the electric force F. Okay, when do we say that the electric potential energy is decreasing? All right, it is decreasing if the charge Q naught is moving in the same direction as the force F. So this is important whenever you want to describe what is happening to the uh, electric potential energy in relation to the direction of the force as well as the direction of the displacement. Alright, we now talk about the electric potential energy considering several point charges. But first, let's introduce this equation. The potential energy U when the test charge Q naught is at any distance R from a center charge Q. Okay, so we determine the potential energy denoted by capital U as the product of K times, all right, the center charge big Q and the test charge Q naught divided by the distance R. All right, the distance R is the how far the big Q is from the small q, all right, or Q naught. So this is only if there is only one center charge big Q. Okay. Also, it says here that that equation is valid for any combination of signs of positive, of big Q and small q. So they can be both positive, they can both be negative, or one is positive, one is negative. But the result for uh, the electric potential energy can either be positive or negative. All right. It says here that the potential energy is positive if the charges have the same sign. Okay, and negative if they have opposite signs, of course. All right. So, what if there are what do you call two or more uh, center charges? How do we determine the total electric potential at a given point, like what is shown in this diagram? Okay, we have Q1 as one of the center charges, another center charge Q2, and another center charge Q3, and there is a test charge Q0 located at a distance R1 from center charge Q1, a distance R2 from the center charge Q2, and a distance R3 from center charge Q3. Okay, so what would be the total electric potential energy of this test charge as a result of uh, having these three center charges, Q1, Q2, and Q3, right? Since electric potential energy is not a vector quantity, it is in fact a scalar quantity, so it goes to show that in determining the total amount of potential energy, okay, at point A, we simply add this individual electric potential energy due to each center charge, just add them algebraically and not vectorially. Okay? And this is expressed in this equation. Okay, the total amount of energy, potential energy at a given point, such as point A in the diagram, is just equal to K times, okay, the given test charge Q naught multiplied by quantity Q1 over R1 plus big Q2 over R2 plus big Q3 over R3. In our diagram, the center charges are denoted by small q, but I'm using here the big Q, okay, referring to the center charge. All right. So anyway, there's no problem in distinguishing between a center charge and a test charge because a test charge is always denoted by Q's of O or Q naught. All right. While center charges, okay, may be expressed in terms of small q but with certain subscript number 1, 2, 3, and so on. Or sometimes they are denoted by big Q with subscript 1, 2, 3, and so on. So this is the formula when you want to determine the algebraic sum. Okay, not vector sum but algebraic sum, all right, of the individual electric potential energy at any given point. We have been discussing about electric potential energy, right? There is an equally important concept which is called electric potential, okay, also known as voltage. So when you say electric potential or voltage at any given point in an electric field, okay, it simply means the amount of electric potential energy denoted by capital U per unit charge or Q naught, which is associated to a test charge at that given point. Okay, the formula for voltage or electric potential, capital B is equal to mu U, capital U divided by Q naught, or if what we are after is the electric potential energy U, then we just multiply Q naught by the given voltage. And in the system we call SI system, the unit for electric potential or voltage is of course the volt. This is in honor of the Italian scientist Alessandro Volta. Okay, and the equivalent of 1 volt is simply equal to 1 joule per coulomb. Okay, in the SI system, that is. And sometimes you also come across with such notation as B sub AB. All right, this in fact is simply the potential of A with respect to B, okay, or the difference in the potential of point A with respect to point B, sometimes written also as B sub A minus B sub B. And this potential difference, okay, at point A with respect to point B is just equal to the amount of work done by the electric force when a unit charge is moved or moves from point A to point B. We'll always have this kind of notation, okay, in our examples of problems related to electric potential. All right, so how do we find the potential uh, V, all right, or electric potential V, sometimes called voltage, due to a single point charge, capital Q? Okay, so if it is the center charge that is given, all right, there is a formula that we can use directly to determine the amount of electric potential or voltage. Okay, this is taken from this original formula for mu, which is K, capital Q multiplied by Q naught divided by R, all right, and this results to B, or voltage, being equal to mu or U divided by Q naught, okay, which actually is equal to K times big Q, or center charge Q, divided by R. So that is when we want the value for voltage in terms of the center charge, capital Q, and how far the point is, okay, the point from the center charge regardless of the test charge Q naught. So we don't need the value for Q naught to be able to define a given electric potential or voltage at any given point around the center charge big Q. Okay, so in this formula, okay, the letter R is the distance from the point charge Q to the point at which the potential is being evaluated. Also, just like electric potential energy, okay, capital V or voltage also has a certain sign, either positive or negative. So that depends, of course, on the sign of the big Q. If big Q is positive, the potential that it produces is also positive at all points, that is. But if big Q is negative, it produces a potential that is negative everywhere. Now, in either case, okay, we say that the voltage is equal to 0 at a distance equal to infinity. Okay, an infinite distance denoted by this sign infinity. Okay, distance from the point charge. So notice that voltage or electric potential, just like electric field, okay, is independent. Okay, does not depend on the test charge Q naught. Okay, that's true also for electric field, if you still remember. Both electric fields and electric potential do not depend on the presence of any given test charge Q naught. Okay, what matters is uh, what we call the presence of a center charge, big Q, because after all, it is the big Q, okay, that owns the electric field. All right, so now what happens if uh, we have a collection of point charges? Okay, in other words, we have 2, 3, 4, and so on number of center charges. What do we do to determine the electric potential at any given point, okay, around this several point charges? So that formula to determine the total electric potential is expressed in this equation. Okay, it is equal to, of course, K is constant, and then multiplied by quantity big Q1 over R1 plus big Q2 over R2 plus big Q3 over R3 plus and so on and so forth. Okay, so this just looks similar to the formula for determining the electric potential energy whenever there are two or more center charges. Except, of course, here uh, you don't see the square. All right, you don't see the square of the distance r anymore. Okay, now some important thing to remember. Okay, we always emphasize this. There doesn't have to be a test charge Q naught at a given point for a potential V to exist at that point, right? Obviously, from the formula, you don't see the symbol Q naught anymore. Why? Because it has been cancelled out. during our derivation, when we divided, okay, the formula for electric potential energy U divided by Q naught, we were able to cancel out Q naught. And that simply means that the Q naught does not or is not important in determining the total electric potential at any given point. Okay, and that's also true. That's also true for electric fields. Okay, we have been emphasizing that time and again that the electric field, net electric field, also does not depend on the presence of a test charge. All right, so we are now. So we now have our first question, which is a conceptual question. Okay, it's about the accelerations of positive and negative charges. All right, a positive test charge is released from A and accelerates towards B, shown in the diagram. Upon reaching B, the test charge continues to accelerate towards C. Okay, assuming that only the motion along the line is possible, what will a negative test charge do when released from rest at point B? All right, so that's clear. In the case of a positive test charge, okay, released from point A, it accelerates towards B, and then it accelerates further towards point C. How about if the test charge is a negative test charge? Okay, how will the negative test charge behave? So we said that a positive test charge accelerates from a region of higher electric potential towards a region of lower electric potential. Okay, as shown again here. Okay, the arrow is directed towards or directed from the lower potential to a higher potential. And a positive test charge will accelerate in the opposite direction. When it is released at point A, it goes, okay, accelerates towards point B, and then further more it accelerates towards C. Is that the case also for a negative test charge? The answer is it's not the same. Okay, a negative test charge accelerates from a region of lower potential towards a region of higher potential. So when released at point B, okay, the negative charge will accelerate towards point A instead of accelerating towards point C. Okay, from lower potential to a higher potential. That is our answer. Alright, this is now our first numerical problem. A proton whose charge is 1.602 times 10 to the negative 19 coulombs moves in a straight line from point A to point B inside a linear accelerator at total distance d equals 0.50 meters. The electric field is uniform along this line with magnitude E equals 1.5 times 10 to the 7th power volt per meter. So that's another unit for electric field, volt per meter. Okay, which is also equal to, of course, 1.5 times 10 to the 7th Newton per coulomb in the direction from point A to point B. We are asked to determine letter A, the force on the proton, and letter B, the work done on it by the field, and letter C, the potential difference B sub A minus B sub B. So, our first question will be answered by this simple, okay, solution. We will consider the force to be in the same direction as the electric field. Okay, and the magnitude of that force is equal to the product of the charge Q multiplied by the electric field that is given. All right. So substituting, we have the value for the charge in coulomb, 1.602 times 10 to the negative 19 coulomb, multiplied by the electric field, which is 1.5 times 10 to the 7 Newton per coulomb, and we get the value for the force. Okay, the magnitude of the force F equals 2.4 times 10 to the negative 12 Newton. The unit coulomb cancels out. So that answers the first question, letter A, which is the force exerted by the field on the proton. And moving on to answering letter B, all right, okay, we are asked to find the work done on it by the field, okay, and since the force that we earlier computed is constant and happens to be in the same direction as the displacement, so the work done must be positive, which is just labeled here as the work done in moving the proton from point A towards point B, and it's equal to the product of the force F times the displacement d, or 2.4 times 10 to the negative 12 newtons, times the given displacement 0.50 meters, and we get this work done equal to 1.2 times 10 to the negative 12 joules. Okay, and just to show you that another unit for work, all right, in terms of what we call electron volts, all right, which is the work done actually in or associated to such particle like an electron or a proton. What we do is just multiply the amount of work done in joules by the equivalent. All right, 1 electron volt is just equal to 1.602 times 10 to the negative 19 joules. Right? So that cancels the unit joules, and we will multiply these two values. I mean, it's actually dividing 1.2 raised to the negative 12 divided by 1.602 times 10 to the negative 19. Okay? Leaving behind the unit electron volt. And the value is 7.5 times 10 to the 6 electron volts, which, again, expressed in a bigger unit, which is MeV, or million electron volts. So we just have 7.5 million electron volts. And of course, answering letter C, what is the potential difference B sub A minus B sub B? Okay, we use that definition for potential difference. B sub A minus B sub B is also the amount of work done on the proton, okay, by the field in moving it from point A to point B and dividing it by the amount of charge Q, okay, charge proton. So we have 1.2 times 10 to the negative 12 joules, which was earlier computed, divided by the amount of charge of a proton, okay, and the result is 7.5 times 10 to the 6 joules per coulomb, also equal to 7.5 times 10 to the 6 volts. But again, just to eliminate this, what you call powers of 10, we express our unit for voltage in terms of megavolts or million volts. So we have 7.5 million volts. Our example number 2, which talks about the potential of a point charge. Using a zero reference potential at infinity, okay, determine the amount by which a point charge of 4.0 times 10 to the negative 8 coulomb alters the electric potential at a spot 1.2 meters away when the charge is letter A positive and letter B when it is negative. So in our drawing, okay, we already stated earlier that for potential or electric potential at a distance r equals infinity, we say that the electric potential is zero. So At a given point r, 1.2 meters away from that center charge or point charge, okay, how do we determine the electric potential if the charge happens to be a positive point charge? And what if it is a negative point charge? So, to determine the electric potential at exactly the same point, okay, for a positive test charge, we have the formula, of course, kq divided by r. So we just multiply 9 times 10 to the 9 by the given point charge, positive 4.0 to the negative 8, okay, and divide it by the given r of 1.2 meters. So we get this answer, positive 300 volts. Now, if the point charge happens to be negative but the same magnitude, what we get is the same magnitude of volts or voltage equals negative 300 volts. They only differ in terms of the sign. So that is our answer to this kind of question. Okay, this is now problem number 3. The potential due to 2-point charges. Okay, so an electric dipole consists of 2-point charges Q1, which is positive 12 nanocoulomb, and Q2, which is negative 12 nanocoulomb. They're placed 10 centimeters apart, as shown in the diagram. Compute the potentials at points A, B, and C by adding the potentials due to either charge. So in our drawing, we have here Q1, which is positive, and 10 centimeters to the right of Q1 is negative Q2. Okay, and we are asked to determine the potentials, okay, electric potentials at different points, such as point A here, okay, which is 4 centimeters away from negative Q2 but 6 centimeters away from Q1. Likewise, at point B, what is the electric potential? Point B, which happens to be 4 centimeters to the left of Q1. And lastly, at point C, which is 13 centimeters away from either Q1 or from Q2. Alright, so what do we do first? We say that at point A, the potential due to the positive charge Q1 can be determined using the formula B sub A 1. Right? This symbol means we are looking for the electric potential due to Q1 at point A. Right? So we use the formula K multiplied by Q1 divided by R1. And by substitution, we have 9 times 10 to the 9 Newton meter squared per coulomb squared multiplied by the charge of Q1, which is already in coulomb, 12 times 10 to the negative 9 coulomb. Divide this whole thing by how far is point A from charge Q1. All right, that is 0.060 meters. All right, and uh, with the help of your calculator, to simplify, we will arrive at this value for V sub A1, 1,800 joules per coulomb, or simply 1,800 volts. It is positive because the charge is positive. All right, now, for the potential due to the negative charge Q2, we can determine that electric potential at point A due to charge Q2 by simply using the formula KQ2 divided by R2. All right, again, substitution. We take note that the charge Q2 is a negative charge, or negative 12 times 10 to the negative 9 coulomb. Divide by the distance between point A, or from point A to charge Q2, which is 0.040 meter. And doing your math, we will arrive at a value for V of A2 equals negative 2700 joules per coulomb, or simply equal to negative 2700 volts. Then, what do we do is to find the sum of the two electric potentials at point A, that due to Q1 and that due to Q2. Add them algebraically. All right, so 1800 volts plus negative 2700 volts, we get for the total electric potential at point A, this is already the sum, that is equal to negative 900 volts. All right, by similar calculations, you can show that at point B, the potential due to the positive charge will come out to be positive 2700 volts. I leave that to you, okay, to show your solution how this answer is obtained. And the potential due to the negative charge will be equal to negative 770 volts. So that if you add the two electric potentials due to Q1 and Q2 at point B, the total will be 2700 volts plus negative 770 volts, or a total of 1930 volts. This is the total electric potential at point B. Okay? And at point C, the same process. Okay? The potential at point C due to the positive charge is determined using the formula KQ1 over R1, which is, of course, the value of K multiplied by the value of Q1, which is 12 times 10 to the negative 9 coulomb, divided by 0.13 meters. Okay, again, doing your math, we will get this answer for the electric potential at point C due to charge, what is this? Charge due to the positive charge Q1, which is equal to 830 volts. All right. Now, the same process, practically the same process, can be used to determine the potential due to the negative charge. Okay, and it will come out to be negative 830 volts. So that the total potential, okay, at point C will exactly be equal to 0. And I'm sure you expected this, because if you notice, point C happens to be at an equal distance from either Q1 and or Q2. All right. So it is at that point where there is no total electric potential. Okay. It is equal to 0. And finally, we come to our last question, problem number 4, the potential due to 2-point charges, okay, which actually earlier we were able to already illustrate. But this time we ask the question, compute for the potential energy associated with a point charge of positive 4.0 nanocoulomb if it is placed at points A, B, and C. Same figure that we use in analyzing example, the previous example actually. All right. So it says that at point C, at points A, B, and C, that is, now we are asked to find the amount of potential energy. All right. At each point A, B, and C, we already knew earlier, we already have calculated the amount of electric potential. So what if a given charge, point charge of positive 4 nanocoulomb is placed at each of those points? What is its potential energy? That is the question. So our solution, for any point charge Q, the associated potential energy is determined by the formula capital U is equal to Q times V. And we use the values of V that we earlier got, okay, in problem number 3. All right. For instance, at point A, the amount of potential energy is just equal to Q times VA. We already knew the value for VA, so we just multiply that by the given charge of 4 times 10 to the negative 19 coulombs. And we get this value. Okay. The electric potential energy is equal to negative 3.6 times 10 to the negative 6 joules. That's at point A. While at point B, using the same formula, all right, but different value for the voltage at point B, we get the charge 4.0 times 10 to the negative 9 coulomb multiplied by 1930 joules per coulomb or volt. We will get this 7.7 times 10 to the negative 6 joules. While at point C, we already knew that the electric potential at point C is 0, and therefore multiply it to any value for Q will give us also an equivalent potential energy of 0 joule. So we just answered question number 4. All right. So this also ends our discussion for this video tutorial. Thank you very much for your indulgence.